Good morning. Thank you, Tom, for that kind introduction. Tom has been a good friend and colleague for a very long time, and I'm going to mention a little bit about that as I move into my talk. It's a great pleasure to be here. I'm honored and pleased to be asked to give the keynote lecture, and I am glad to see the sun shining this morning on the day after our big elections yesterday. You all look awake. I'm not sure I am after all that activity. I and many others aggressively argued for the need for a network, a high-quality network in the United States that would give us information about the chemistry of precipitation and ultimately the chemistry of our atmosphere. Several sites began this network in 1978, September 1978, initially from the state agriculture experimental stations, the North Central Regional Project. There weren't nearly as many stations as there are today, but it was a start, and it's grown into something that, as the last report you just heard indicated, we should all be exceedingly proud of. I am. Ellis Colling gave the keynote address on the 30-year anniversary, and he outlines his history, and you can check that out if you're not familiar with it. So, happy birthday, NADP. 40 years of successful operations. Many features make that success very meaningful. The fact that there's one very high quality analytical laboratory, something that many of us argued for in the beginning, that it would be necessary to have one laboratory doing all the samples and providing that uniform base. That's worked. It's worked very well. So the critically important long-term data that characterizes the status and the changes, the trends in precipitation chemistry, high quality is the feature of these data that are so important, and that's thanks to all of you. But even so, some would say, 40 years, isn't that enough? Shouldn't we stop now? Because you've got 40 years of data, how much more do you need? Arguably, I would say that it's probably never been more important in our country to continue this network of high quality monitoring of the chemistry of our atmosphere through precipitation chemistry than ever before and without interruption. I'm going to come back to that point several times in what I'm saying this morning, and particularly near the end. In some of our most important environmental high-quality long-term records, like the Keeling CO2 record in Mauna Loa, that record, some of you may know, was terminated 6 times. But through perseverance and support, they've been able to keep that record going, and arguably is one of the most important environmental records that we have that tells us what is going on in terms of global climate. This record, I would argue, is in that category. Recently, a colleague of mine in Australia and I published a book about monitoring, and I wanted to review some aspects of that because I think it's appropriate as we think about the future. 40 years is a long time, as I'm arguing, is not nearly long enough. The title of this book is Effective Ecological Monitoring, and it's not a how-to book. It's a book about the philosophy of monitoring, what makes monitoring successful, what makes it not successful, and how does it work in the long term to survive, to maybe initiate and survive. We argue that it isn't long term unless there are at least 10 consecutive years that are monitored. That's our definition of long term. And that there are 3 types of monitoring that are done. One is, well, I just wonder what the ice cover on this lake is going to be like next year and how it was last year. And so I do that because I'm curious. So that's curiosity type monitoring. Then there's mandated monitoring, and NADP falls slightly into that category because in some sense it's somewhat mandated, but not really. The Weather Service is a better example of mandated monitoring. And then question-driven. And I think that's where the NADP monitoring falls primarily. So what makes monitoring successful? In our opinion, we argue first and foremost, good questions. And from the last speaker, you heard that directly and indirectly, that if you're going to keep a system going, it has to have good questions. It has to be driven by good questions. Usually there has to be a good conceptual model. In this case, what's the physical layout, spatial layout of the monitoring stations to cover our country in a way that we think is appropriate. That ties in with experimental design, particularly statistical, and frequent use of the data. I think one of the reasons monitoring is often maligned as being mindless data collection is because the data aren't used. And so it has to be used. And you just saw in the last slide that these data from NADP are being used in a variety of ways. And I think that's one of the reasons that NADP is successful. So scientific productivity and use of the data. And management relevance. And I'm going to talk about that today in terms of acid rain. I'm going to use NADP and Hubbard Brook as examples of the management relevance of the data that we collect long term. And then good data management. The data are collected but aren't available in a reasonable form and time. In other words, if you have to wait 2 or 3 years before you get your hands on the data, if you want to publish something, or you have a question that needs those data, then that doesn't work. So, just like good science, good and successful monitoring needs to be driven by good questions, but things change. And again, my colleague and I published a paper in which we proposed adaptive monitoring, and NADP has done that really very well in terms of these different kinds of monitoring beyond just precipitation chemistry. Mercury and leaf litter is probably the excellent example. So you have your core monitoring program, but you adapt it, maintaining that core, but you adapt it for new questions so that it maintains relevance and urgency at the time. And then don't do science backwards. I know this is a little preaching, but it's something I feel very strongly about. Don't just go out and collect mountains of data, as frankly the eons do, like neon, you mentioned neon. And then, well, what can I do with these data? I have all these numbers I've collected. Do it the other way around. Ask the question, collect the data, use the data to answer the question. Trying to retrofit questions to mounds of data sometimes work, but the possibilities of it working very often are not high. I worked for a very long time at a place in the White Mountains of New Hampshire called the Hubbard Brook Experimental Forest. We started ecosystem studies there in 1963. and have continued them to the current time. I'm currently retired, so I spend much less time doing that, but my colleagues at Hubbard Brook are continuing that effort in a very aggressive way. Hubbard Brook is located in the White Mountains of New Hampshire, sort of in the middle, not really, but in the middle of a large northern hardwood forest bioregion. The vegetation is sugar maple, American beech, yellow birch, some conifers, but that's the mixture of this northern hardwoods forest system. It's a large ecoregion extending through the Great Lakes, much of New England, and down to the stem of mountains towards the south. So it's a large area. In 1963, the 24th of July, we collected our first sample of precipitation, and we were collecting the precipitation not to discover acid rain, but to give us information about the inputs of chemicals to the forest in terms of how the forest might look. The result of that first sample was that the pH was 3.7, and we were shocked. We had no idea that it could be that low, literally 100 times more acidic than we thought it might be, or we didn't know what it might be, but what we thought it might be. And so how could it be that acidic? Where was the acidity coming from? Was this something unusual to the White Mountains of New Hampshire? After all, New Hampshire is the granite state. What? We didn't know. We continued to sample precipitation chemistry throughout the year, and the volume weighted average at the end of that first year was about 4.1. Still very much more acidic than we thought it might be. As you all know in this group, the theoretical acidity for ambient concentrations of carbon dioxide dissolved in distilled water would be about 5.6. That's about all we knew at that point in time, in 1963. So the questions that we were faced included these: how is the acid rain formed? How long has it been like that? And what's the pre-industrial revolution value? In other words, how did it change from human activity? Well, widespread, as I said. Was this something unique to the White Mountains of New Hampshire? And what's the source area? Where's this stuff coming from that's making the acidity? So, as you all know, I'm sure in this audience, but I wanted to review it quickly. Acid rain is actually a very simple phenomenon. With the combustion of fossil fuels, primarily coal, sulfur and nitrogen oxides are added to the atmosphere, and in the atmosphere are converted to two of our strongest acids, sulfuric and nitric acid, which then come back down to the land and water surface as rain, snow, sleet, hail, particles, gases, a variety of wet and dry forms. So that's really what acid rain is. But again, we didn't know that in 1963. Part of this talk this morning is going to include some personal views on what happened during this period of time. I changed jobs in 1969. I had been a professor at Dartmouth College for 8 years, and that's when we started the Hubbard Brook Ecosystem Study. And I changed jobs and moved to Cornell University. And this is a picture of me when I was 10 at Cornell University, starting to collect a sample of precipitation with a bulk precipitation collector at what was called the Ithaca Game Farm, because I wanted to try to understand whether the rain chemistry around the Finger Lakes of New York, which is not very far from here, And I was focusing primarily on Cayuga Lake and Seneca Lake. So I established collectors all around Cayuga and Seneca Lake, and this was one of them at the Cornell University Game Farm location. So this was in 1970. What I found was very surprising and shocking, actually, to us at the time. And the two sites here, numbers 2 and 3, are at the Ithaca Game Farm and the Aurora, the Cornell University Aurora Experimental Farm locations, had just about the same pH plotted here as we were seeing in the White Mountains of New Hampshire. So these 3 lines are for those 3 sites. The one in New Hampshire at Hubbard Brook and the 2 along the Cayuga Lake shoreline, not really on the shoreline, but next to it here. Being about the same throughout the course of this first year when I set up the sites in 1970-71. So that was the first clue that we had that this phenomenon, if that's what it was regional, was not just something located at Hubbard Brook. We published 2 papers, one with one of my students, Charles Cogbill, and another with a colleague of mine, Herb Borman, in which we proposed that the acidity was not regional and was in fact coming from the Midwestern United States, the large power plants where coal and oil, primarily coal, was being burned to produce electricity in states like Ohio and Indiana, Kentucky, and Illinois, and so forth, and that those pollutants were being moved to the east and were falling in our collectors as acidic precipitation, rain, and snow. So that was our proposal. The paper by with my colleague Borman was published in Science, and it caused quite a stir because it was written about on the front page of the New York Times the day before the paper came out in Science. So the publicity on the front page of the New York Times caught all the attention, and probably no one ever read the paper, they just read the New York Times. But one of the things we were arguing was that we had converted local soot problems to acid rain problems by increasing the height of chimneys and smokestacks, putting the pollutants higher into the atmosphere, and then the prevailing winds were carrying them to the east. The data collected by EPA for the period 1900 to 1980 for the height of chimneys and smokestacks is shown here. I apologize for the shows up better than I thought it would. This was my attempt to convert a former real slide into a digital PowerPoint. Still have problems with that. Anyway, you can see 2 important things here. One is the increase in emissions of sulfur dioxide from 1900 to 1980. The total is increasing, at least until 1975 or so, and then declining until 1980 maybe. No air limits on any of this. But the height of chimneys and smokestacks were dramatically changing. So in 1900, the majority of sulfur dioxide was being emitted from stacks that were less than 120 feet tall. And by 1980, did I say 1980? In 1900, less than 120 feet tall. And by 1980, the majority was being emitted from stacks that were much taller than 120 feet, and some of them really quite tall. more than 480 feet tall. So that was a part of the reason why we were arguing that these pollutants were being emitted taller and taller in the atmosphere and converting a local soot problem to a regional acid pollution, air pollution problem. But that caused a great deal of controversy. At the same time, the other paper with Cogbill, we had found some precipitation chemistry collected by Young and Werby, on which they did all the precipitation chemistry, but they didn't do acidity, they didn't do pH. So we decided we would calculate the pH. And so this map, shown here for 1955, 1956, is a calculated hydrogen ion, or pH, map, the first map I know about for the United States, in which we were trying to show the distribution of acid rain in the eastern United States. I think we all understand the importance of visuals, like maps and cartoons, in terms of communicating with the public and the media and with decision makers. A map is a very powerful tool in that regard. I could stand up and talk in 1975 about the pH of precipitation and but to show a map like this for this time and then for 10 years later, in which there were data collected by USGS and by a US Public Health Service and INCAR group, and they had a network, and showing actually that there was a slight increase in intensification and spread, particularly to the west, of acid precipitation. And then 10 years later, in which Tom and I contacted all of the investigators that we could think of and find and locate in the eastern United States, and agencies, state agencies, federal agencies, any and everybody that we could find and think of, and ask them if they had measured precipitation chemistry, particularly pH, and would they share their data with us? And they did. And this was a graph then for 1975-76, using that information. Now, this is a hodgepodge of bulk and wet only, a lot of different people using a lot of different methodologies for the collection of the samples, and all the other things you can think of to criticize this approach. But at least it was an attempt, and there are a lot more points, and with a lot more points, when you draw the isolines, some of those problems disappear in terms of their relevance or importance. So with these three graphs, 55, 56, 10 years later, and 10 years later, the story then starts to become, oh, really? Really? This is what's happening to acid precipitation in the United States, and there might be something to it. However, there were many skeptics, many deniers, many questions, including some real skeptics in the NADP. Challenges about, well, you can't do it that way, or you can't calculate the pH. James Morgan and a student did an error analysis in which they asked the question, can you do calculated pH if you have the rest of the chemistry done well? And they determined error limits or uncertainties around that. So that came out just as we were doing this, and that gave us support that we were on the right track. However, as Tom and I said in the paper in 1981 in Atmospheric Environment, quote, unfortunately, even today, it's 81, there is no detailed picture of the chemistry of precipitation over Canada, the United States, and Mexico. And this is after NADP had started in 78. There still was no picture. And these three maps that I've shown you were not NADP data. There weren't maps generated by NADP at that time. So a little of that history about where this really strong environmental issue was going at that period in time. A lot of other stories and politics that I'm not going to get into, particularly since I stayed up too long last night watching the voting. I've never written a paper like this one. I'll probably never write another paper like this one. The title of this paper was Red Herrings in Acid Rain Research. Written by a postdoc, a colleague, and myself, published in the S&P in 1984. And we indicated 5 things that were being said, whether there was any information for them or not, but they were being said, like, bog lakes have been acidic for thousands of years, thus the acidification of lakes is not a recent phenomenon. Or the early methods for measuring pH are in error, therefore no statements can be made regarding historical trends. I've shown you my attempts to look at historical trends. Acidification of lakes and streams results from changed land use practices and not acid deposition. The decrease of fish populations is caused by overfishing, disease, and water pollution, not acidification. And because lakes that receive identical rainfall, they talk about snow, can have considerable different pHs, regional lake acidification cannot be due to acid deposition. Red herrings. We looked into all of these and wrote this paper addressing these red herrings and looked into the explanation for why acidification was not occurring. And it was a very, very controversial issue at this point in time in the early 80s during the Reagan administration. And this is what we scientists do a lot of. We spend a lot of time dealing with explanations that may be even irrelevant, let alone not correct or valid. And where do we come out with that? How many of you read the book Merchants of Doubt? A few. I would urge you all to read Merchants of Doubt. Merchants of Doubt has a very simple premise, written by 2 historians of science, Orestes and Pomeroy. The very simple premise is that if you create doubt, and it's very easy to create doubt, then it raises and delays all the issues associated with whatever environmental issue you might be talking about. And they talk about tobacco, first and foremost, DDT, acid rain, and climate change. You might say, well, my grandfather smoked until he was 90, didn't seem to affect him any. So obviously, smoking doesn't have any harmful effect on your health. Wrong. But that doubt inserted then is a way in which you can delay and keep us scientists busy for a very long time. At any rate, so there was a lot happening in these times in the 80s, a period I call the 1980s war on acid rain. The question about were the pollutants coming from west to east with prevailing winds was a vexing one. We could see the plumes coming out of large chimneys and smokestacks in the Midwest, but it was very difficult to follow them at that time, and particularly to analyze them and whether they were actually affecting the chemistry of precipitation. I want to tell you a little story. It's true, but you probably won't believe it. Working with colleagues at INCAR, Al Lazarus in particular. We flew above these power plants in the Midwest in a small plane, trying to follow the plumes, holding collectors out the open window of the small plane, trying to collect samples. We also had a van on the ground that was trying to follow along under the plume and hoping that it was going to rain, and if it did, you would run out with your collector and try to collect a sample of the rain to see if that was being transported. Tom was actually on the ground crew for a couple of years, as I recall. That's what we did. That's all we had available at that time. We got more sophisticated later with stable isotopes and so forth, but that's what we did. What we found, however, was that these are long-term data from Hubbard Brook shown here, that if we calculated the sulfur dioxide emissions from the source area, that was not easy. We had to use the high split 4 model of Drexler and Hess to track the trajectories of storms that actually produce precipitation right in our Hubbard Brook collector. We initially did all that by hand, and it turned out to be impossibly difficult. But with their model we could, and then with Swindler's cluster model we could then determine what our source area was for sulfur dioxide. So plotting that source area for 24-hour source sulfur dioxide emissions against the sulfate that we actually collected in our collector at Hubbard Brook, we got this relationship. Well, the first 1964 to 1969, the amount of sulfur dioxide emissions was not going down much. If anything, it was going up during part of that time. So those aqua points don't show any relationship at all. They're essentially vertical. But then we got into 1970, 1980, the next decade when the amount of emissions were declining, the dark blue points are starting to show a relationship, and then 1980 to 2000, the red points, and at that point, all of those points give us an R square of 0.8. So clearly there was a strong relationship between the emissions. Again, we didn't know that. Where's this stuff coming from? And all the deniers are saying, well, it's not coming from us. We didn't do it. It's not us. Did you ever hear that story today about climate change? No, not us. That's what they were saying. So we had to do this kind of stuff to try to answer the questions about where it was coming from. And heading back maybe toward PIR, pre-industrial revolution limits. So that kind of a graph relationship, again with the long-term data, and continues to at the current time, but that wasn't valid what I'm showing here. So 1964 to 2000, that's a pretty long time to collect data, to get one graph to try to relate to this transport versus deposition. Calculated that the amount of sulfur, sulfate, I was collecting in my collectors at Hubbard Brook relative to the amount emitted in the source area coming to Hubbard Brook over the course of a year was 0.001%. I was collecting 0.001% of the sulfur emitted in my collector, and I still could get a relationship like that with an R square of 0.8. I don't understand how that works. It's too complicated for it to work like that, but there are the data. So we started the Connecticut hillside in the autumn of 1976, and yes, Tom is one of the longest operators in the network. He's been running the site for 42 years, so you need to check your record somewhere about that. But anyway, Tom actually helped pick out the site if he didn't pick out the site, and these are what's being measured now at New York 67. But it started in the autumn of 1976. So Tom has worked for me and with me and is a dear friend to me since 1976, a long time. So that site grew out of that 1970 effort when I put up bulk collectors at Aurora and Ithaca Game Farm that I mentioned before. So this is the way the site looks if you've not been there. So I wanted to just show you a few of the long-term data from this site. So this is hydrogen ion, and let's start with the lower graph. My pointer, I don't think that's too much. So anyway, the lower graph. It shows Aurora and Ithaca. Those are bulk collected samples, whereas the other points are wet only. So that's a difference, but nevertheless, still has a very high R square. The data for just the NY67 is shown above and has a little higher R square. But however you want to deal with bulk and not bulk, we've tested that at Hubbard Brook, not here in Connecticut, but we have at Hubbard Brook. The record goes from 1970 currently. A decline of about 80%. A real success story. We have reduced the acidity of our precipitation by a huge amount. But I'm going to come back to that. Here it is for sulfur dioxide. Again, Aurora. Aurora is on a farm. It's an edge of a farm, so it's always contaminated by farm dust and animals. So the Aurora site's a little higher, but still the R square for that whole record is pretty good. But for the site, it's very good, and a decline here of 78% over this long-term period. Nitrate, same kind of pattern. Aurora and Ithaca fall more on the line than the other two, a decline of 59% over this long-term period. And calcium, note the bulk collectors for Ithaca and Aurora clearly contaminated by farm dust. And then after that, the data are quite robust, except at the beginning of the record for 67, there's a lot of wiggle in the beginning. And I'm going to come back to that in a moment. But the decline is about 33% there. I mentioned the maps and the talk just before this one, you saw maps. But these maps are so important. The long-term trends, so the two things about NADP, the long-term trends, which I've just shown you just for the site that Connecticut Hill that we run, but then these maps for the whole network. So the pH from 86, 96, 2006, 2016, that's a powerful visual image. To a politician or to the media, they get it. I mean, there's been a huge decline. And the whole eastern United States, which was essentially red or pink, is now not. So that's a really important message from NADP that only could have been shown. The long-term data from Hubbard Brook are longer, but there's only one site. So this is a powerful message. So that's pH. There's sulfate, same pattern as pH. It should be because they're related. Nitrate, again, same pattern. It should be because they're related, because we're dealing with both of these acids, sulfuric and nitric. And for calcium, yeah, well, that takes some looking at, and some thinking about, and some pondering to think about calcium. It's beyond what I have time for today. But I'm arguing these maps are really very important. So the Hubbard Brook experimental forest, the White Mountains in New Hampshire, is a large bowl-shaped valley. It's drained by a river, but in New England we call rivers all kinds of things, and in New Hampshire it's a brook. So it's a fifth-order river, that's Hubbard Brook. We have open areas throughout the forest that are cleared and have precipitation collectors, both bulk and NADP. There's only one NADP site, but these are the way it looks summer and winter. The record, as I said, starts 1963, so it's older than NADP. So if you look at magnesium and calcium in the top graph, I'm also interested in stream water chemistry, but I don't have time to talk about that today. There was a sharp decline in calcium and magnesium prior to the time NADP started. So we missed some important information by not starting NADP quicker than we did. I'm being facetious, but we missed that information because look, it's been relatively flat ever since, and that's what the data from the Connecticut Hill site shows as well. The value of long-term data. Why? Well, one possible reason is this. These are EPA data for 1970, 1987, and primarily because of the 1970 Clean Air Act reducing particles, which contains a lot of this calcium and magnesium that is added to the atmosphere. Big decline in industrial processes, 76% decline. Fuel combustion, 61% decline. Solid waste incineration, 73%, and so forth. Big declines just during this period when the decline in calcium and magnesium in precipitation was declining. So there again, the precipitation chemistry that we collect and that we analyze tells us something about what's going on. We do our science to connect it with what maybe the sources are, and we start to get a picture that makes sense. Long-term data from Hubbard Brook show a lot of interesting things that I don't have time to talk about today. I thought I'd show you a picture of the nitrate concentration. Now, this is bulk precipitation starting in 1964 and going until the current time. We're currently appreciably less nitrate in precipitation today than we were when we began. We thought we were pretty low when we began. In fact, the first 6 years of our collection showed an increase in nitrate concentration. We wrote a paper about it. We thought, wow, that's really interesting. 6 years, the nitrate concentration is going up. We should document that. We did. Well, that paper is of historic value only because that isn't what happened long term, as you see. It's a long bell-shaped curve, and the concentrations now are about like we projected they were in 1940. If we look at the trajectory for acid rain at Hubbard Brook, it looks something like this. We started in 1962. That's the X at the end of the dotted line with an arrow on it. And then 64 right below it. And then the numbers 65, 66, 67, 68, 69. This is the acidification period. We caught just the end of it. We've been doing Hubbard Brook for 5 years. And we just caught the end of it. We needed a lot earlier data. We needed a lot more than our 55 years. I'm greedy in terms of long-term data. So that was the acidification. It turned around, and in the hysteresis, moved down 70, boom, 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 right down to the current point. And is headed for pre-industrial revolution values, or what we found recently, probably lower concentrations than pre-industrial revolution values, something we call pre-acid deposition values, PAD. Because of the Clean Air Act's success in removing acidity from the atmosphere. That's a huge success story. So this is the acidification curve for Hubbard Brook. The acidity of precipitation has decreased at Hubbard Brook by about 80%, also like Connecticut Hill. The Clean Air Act 1970 shown here, the Clean Air Act amendments, which for the first time in the U.S. focused on reducing acid rain, 1990. Took 5 years to implement the 1990 Clean Air Act, so that increase after the Clean Air Act was during that period. It shows how sensitive our systems are and these monitoring networks are to those kinds of political actions, and then currently down to the current value. A huge success story, but if we look at, and we've been trying to project, as I said, with more data, back to 1900 or pre-industrial revolution. One of the questions was, what was it like in 1900? So 3 colleagues and I went to several of the most remote places on the planet that we could find to do precipitation chemistry. We went to the southern tip of Chile, the southern tip of Africa, an island in the middle of the Indian Ocean called Amsterdam Island. Takes a month by ship to get there. A remote place in China, a remote place in Australia, and so forth. And we ran precipitation chemistry sites at those remote locations for 10 years, just to get the number of what the acidity of precipitation might have been prior to human activity. And the number we come up with is 5.1 as a background number. But 10 years in all those sites to come up with 1 pH value. And we had to have that information. So that's where the red dot is on the, sorry, I can't point at this point, the red dot is on the pH graph. That's the start for the pH. And then some of these historical data that I mentioned before, we put on there, not to use the projections and trends that we've done, but just to see how they agree with some of the historical data, and they agree quite well. So it shows the sharp decline in pH in the 50s, the early to mid 50s. So that's when we think precipitation as a phenomenon started in the eastern United States. The sulfate curve, look at the blue one, the green one is stream water. Sulfate from 1900 to current time, you can see the buildup, which is in this model period from 1900 until our measurements started in 1963. The Great Depression in the 30s actually shows up as a dip in terms of the amount of sulfur dioxide that was emitted, because there was a lot less coal and oil burned during that period of time. So that's for sulfate. And then this hysteresis, now extending it back to 1900. The other one I showed you was just for the period of our study. So going back to 1900, the line progresses up according to this analysis that I did. And then you see the hysteresis and coming back down, but to a value lower than PIR, to a value of PAD. So the system is more dilute than what we estimate was the case for pre-industrial revolution. Okay, so I think you're all familiar with NAPAP. NAPAP was actually a strong supporter of NADP in terms of need for additional sites and funding for some of those sites. But NAPAP concluded that forest soils in the U.S. had not been impacted seriously by acid rain. It's in the report in 1990. Well, we looked at that carefully at Hubbard Brook. With these strong acids fall on the forest ecosystem like the one at Hubbard Brook, the hydrogen ions exchange with calcium and magnesium. They liberate aluminum into the dissolved form, and then stream water carries away the calcium, magnesium, and aluminum that has been either exchanged for or mobilized. We calculated that about 850 kilograms of calcium per hectare have been deleted from soil pools at Hubbard Brook during this period, 1940 to 1995, about 50 years or so. A lot of calcium. Actually, our more recent numbers indicate that it's probably larger than that. And now many others that paper was published in 1996, and now there have been many other papers that have shown similar kinds of calcium declines. With this back trajectory of our trends to 1900, we can calculate the total loss of calcium or sulfur or whatever, as I showed you very briefly. And one of the really interesting findings is shown in red. 60 years of acid rain had a calcium stripping impact at Hubbard Brook, equivalent to 2 deforestation experiments that we've done. Some of you may know about the experiments we've done in Watershed 2, where we cut all the forest and then treated with herbicides for 2 years. So it was an extreme kind of treatment to remove the vegetation for 3 years. So this 60 years of acid rain had a greater impact on the calcium stripping than 2 of those would have done. To me, that's amazing. I had no idea that acid rain had that large of an impact. So where do we go from here? I would argue that acid rain continues to be a very significant environmental problem. We have reduced the acidity of precipitation by a huge amount, 80%, within many sites in the eastern U.S. from the NADP network and at Hubbard Brook. But it's emerging in other places like China and Southeast Asia. China has a major air pollution problem in terms of particulates. Those particulates are loaded with acid neutralizing capacity, and as those particulates are stripped from the air in China and other places that have that problem, like in Southeast Asia, then you're left with an acid rain problem, and potentially a very large acid rain problem. There's now been several papers published by Chinese and other scientists indicating that this is a very large worry in terms of what is going to happen globally in terms of acid rain. The increased importance of calcium and magnesium as a buffering agent in very sensitive systems like Hubbard Brook. And with the buffering capacity so depleted, in Hubbard Brook, it's more than 50% of the exchangeable calcium has been stripped by acid rain in this 50-year, 60-year period. That's a lot, which then leaves the system much more sensitive. And even though there's less acidity, if the system is more sensitive, potentially that less acidity has more impact on it, right? You with me? And if we were to increase now the acidity through rollbacks done by our federal government on air pollution, rollbacks of the MATS program, the cross-state pollution program, those are already occurring, and they had huge additional decreases in sulfur emissions. Title IV, the Acid Rain Act of the 1992 Amendment, so far has not been challenged, but if those were to happen, why some of us stayed up last night and watched the elections, then if the acidity goes back up, falling on now more sensitive soil ecosystems, where does that leave us? I don't know. But potentially, it could be a problem even worse than we thought it was 20 or 30 years ago when the acidity was higher. So think about that one. We don't know. So what if the regulations are rolled back? The New York Times reported in the last month or so that there have been 76 rollback of environmental regulations in the United States, 76. So there's this constant tug of war now going on. Do we want cleaner air? Do we want dirtier air? Do we want sensitive systems that are being impacted by increased amounts of acid rain? Why do we need NADP? More than ever, we need to know. We need to know in the next 5 years whether sulfur as sulfate and nitrogen as nitrate and ammonium, whether those are changing and which way they're changing. Are they going to continue to go down, or are they now going to go back up? We need to know. So that's why I said in the very beginning, maybe never before in the history, our 40-year history of NADP, have we needed this network more than we do today. And it's high quality, impeachable quality standards for answering really critical questions of that sort. Questions that affect not only our livelihoods, but how we live our lives and the quality of our lives. This is no time to eliminate or decline in NADP. NADP is so complicated, so many sites funded in so many ways, at so many locations, held together by a structure and a central laboratory, that if it were ever to be disbanded or lost, to me, as one of the people that helped originate it, I can't imagine it ever being started again. It's just too complicated. So don't let that happen. Don't let that happen. Ellis Coling 10 years ago said 30 years down and 100 to go. I think that's wrong. I think it's 40 years down and never to stop. Never to stop as long as it's driven by questions. And that's what we in this room do. We ask the questions that drive the need for the monitoring network to answer those questions, which are so important. Tom had handed me, just before I came up here, this new issue of the Adirondack magazine. I haven't seen it, but right at the top, the headline is "Acid Rain Returns." I haven't read the article, but I'm not quite sure what they're talking about, but I think I know what they're talking about. So we don't want acid rain to return, do we? Anybody here want acid rain to return? I spent a good part of my professional career fighting the deniers and the skeptics and saying, well, I don't know, but this is what, I'm a scientist, this is what the data show, and this is what I know from the data. I don't want you to have to go through that again. That was not pleasant. Finally, it takes a long time. From discovery to political action was 27 years. Discovered in 1963 to political action in 1990. To make that happen requires fundamental information, fundamental answers to how did it get that way, where did it come from, how long has it been like that, all those things I mentioned in the beginning. A lot of effort. I say it took 3 US presidents, 1 pope in 27 years. Jimmy Carter started a memorandum of intent with Canada because there was a huge controversy between Canada and the United States about who was giving whom the acid rain or the sulfur in the precipitation. With the Sudbury copper nickel smelter, they had a huge source, but it mostly wasn't coming across the boundary our way, but they started this effort to do the memorandum of intent to negotiate that. When the Reagan administration came in, one of the first things they did was they shelved the memorandum of intent, literally shelved it. It was 15, 20 feet long shelf space. Yeah. Study instead with NADP, and in 10 years we'll have the answers we need. We spent $570 million with NADP, NAPAP. The 1990 Clean Air Act amendments were signed into law before NAPAP's final report was ever issued. Bush the senior, one of the first things he said publicly was, when he was elected, was, we have to deal with this acid rain problem. It's going on long enough. His Secretary of State, Baker, said exactly the same thing. His administrator for the EPA said exactly the same thing. So he signed it into law in November of 1990, the 1990 Clean Air Act amendment. The Pope, I and some others met in the Vatican for a week, discussing these issues. We gave our report to the Pope, John Paul II. He was very kind and gracious. He listened, and then he issued an encyclical. Probably the encyclical did more in terms of global political action than any science I ever did. But thank you for doing that. That was important. So we don't want to go through that again. I don't know if it's worse than it was in 1970 or 1980 or 1990 when we passed the Clean Air Act amendments, but we don't want it to go back up. I don't want to breathe dirty air. I don't want my systems to be degraded any more than they are. I fought long and hard, and I will continue to fight long and hard, and I urge you to join me. Thank you. If there are questions,
we have time. People want to ask Dr. Likens a question.
I have lots of stories I can tell.
He said if there's no questions, he'll tell some old stories. Anybody want to ask Dr. Likens a question?
I sort of have one. I don't know if you have an opinion on this, but what do you think about the way that they dealt in 1990 with emissions in terms of, it was posed as create a market for emissions, to trade them as opposed to just a regulation, you have to reduce to this level. Do you think that's an effective approach? I mean, is that something we could use, say, for carbon or other things?
Yeah, I do have a thought about that. And in fact, I was involved in that. When George H. Bush, came, both the House and the Senate had overwhelmingly passed the 1990 Clean Air Act amendment language. Overwhelmingly. Just a few people didn't go along with it. So it came to him, and he was to sign it. And he had said, as I mentioned to you, that we've got to deal with this acid rain problem. It came to him to sign it, and he started to waver, started to falter. And just at about that time, the Environmental Defense Fund came up with this trade-in concept, that you could trade emissions from dirty plants with clean plants and make money on it. And with that economic incentive, he signed it into law. At the signing ceremony, how many scientists do you think were there? How many do you think? 1? 2?
0.
2? No, 0. How many EDF people do you think were there? About 4. So that had the huge impact in terms of getting them to sign it. The potential for trading carbons is not the same. I actually published a paper with this on this. the biogeochemistry of sulfur is that you can combust as it goes up a stack and goes somewhere and comes down within a reasonable distance, maybe thousands of kilometers, but a reasonable distance. But with carbon, it goes up a stack, it's mixed in the atmosphere, and may end up in Antarctica or wherever. And so the trading of dirty and clean plants make no sense at all from the biogeochemical point of view. So I think in terms of carbon and climate change, it has to be much more something like, and I don't know the right answer, but much more something like a carbon tax. I'm teaching a course at the University of Connecticut, and we had a speaker last week from Yale, and Yale University has this new system in which it's a carbon program in which they're assigning carbon. They put a value on carbon, $40 a ton, and so every academic unit is assigned so much carbon because all the buildings are monitored, or the majority of them are monitored for energy. And so if they don't meet that goal that they set collectively, then they have to pay, the department has to pay the administration. If they get under, then they get money from the administration. So they've just started this. It's been 15 months going. It's going to be very interesting to see how it works. But if it works, Nordhaus, who just won the Nobel Prize in Economics, is a Yale professor, and he was one of the guiding people in making this happen at Yale. But if this works, then all of our universities and other groups are going to have to do that. That's a long answer to your question. Thanks. Something very much on my mind.
Yeah. Does anyone else have a question that they'd like to ask?
Over here, John.
Thank you very much for your presentation today, especially the hard work in your career. And I appreciate you mentioning merchants of doubt and just this entire strategy to dispel what we know because of all the things we don't know. And so in your experience in working with all of these policymakers and people and getting your science communicated, how do we help create that culture, in your opinion, of instead of having doubt upon what we know, let's go ahead and go forward with what we know and not doubt that part, understanding that science is not perfect, but we need to go forward with what we know.
I don't know the answer to that question. I probably should have said it up there when you couldn't hear me. I don't know the answer to that question. But it's something that I have pondered a lot. And there's just so many dimensions to that question. In the acid rain debates, when we came right down to the point where the Bush administration was going to have to deal with this, and then ultimately did, the National Academy of Sciences, which usually is a very conservative group in issues like this, came out with a statement very much like the one you just said, that we're never going to know all the answers, we're never going to know everything to the nth degree, but we know enough now that it makes sense that we take action. The precautionary principle, it's called. And so they came out with that, they gave that to the Bush administration as a white paper when they came into office. I think from a science point of view, I think we often know plenty of science to provide the advice, and we don't make the decision. The decision makers do that. But I think the decision makers, and we're seeing that in this country right now, I don't want to get too political, but right now, in terms of these tribes that we're in, and so you're either a Democrat or Republican or whatever, and you don't talk to anybody else, you hate everybody else, and we don't make any progress when we're like that. So, Merchants of Doubt is a story about, starts with tobacco, and the scientists for the tobacco companies were starting to see that tobacco has health problems, causes health problems. And they were bringing this to the higher levels in the companies, and the companies said, oh boy, that's going to cost us a lot of money. So they organized a meeting in Manhattan, and they brought in the top PR firm in the country. It's all in the book, you can read about it, and said, we have to deal with this in some way. And so the PR company said, fine, we'll just generate doubt. That's all we have to do. That's all they did. And then they went ahead and did the same thing with secondhand smoke, DDT, acid rain, climate change. And you're reading this book and you say, why? How does this work? How do they do this? And there were 4 prominent physicists that were advising them throughout all this process. Why? Why would you do this? And these 2 authors answer that question from their point of view in the last chapter, and I'm not going to tell you what they said, because I want you to read the book. But I don't know the answer to that question. Can I tell you one story, and then I'll get too far out? I led a small group. Booker Monin isn't by any chance here, is he? I led a small group to the White House in September 1983, and we briefed President Reagan and the full cabinet on acid rain. I don't think that had ever been done before. And had a full hour with them. And we described what acid rain was and the problems it's causing and what should be done about it. And at the end of the presentation, 2 things happened. I happened to be standing at that point in time close to President Reagan. And one was, he leaned back in his chair and he said, quote, well, gentlemen, and there were many women there, well, gentlemen, it is clear to me that my undergraduate education did not prepare me for such complicated issues, unquote. And I thought, good grief. And then I thought, where did he go to undergraduate school? So that little story tells you a number of things. The other little story was that some of you, not many of you, are old enough to remember that he loved jelly beans and he had a habit of having a apothecary jar of jelly beans for any meeting that he ran. And the jar was on the table. And so he offered us a jelly bean. And so I reached into the apothecary jar and I grabbed a whole handful of them and I put them in the blazer pocket I had on. And thank you. And I gave them as Christmas gifts. And I gave one to my mother, who lived to be 204. And she thought the jelly bean from President Reagan was the most wonderful gift she ever received.